A classical problem about finding the area of a region that has a curve to it is one of the types of problems that actually initiated the development of calculus. We know how to find the area of, say, a rectangle or a triangle or a polygon. We also know how to find the area of a circle. But what if we want to find the area of an enclosed region where the sides of the enclosed regions are curvy? Well, it took a while to look at the different aspects of this situation and come about the development that ultimately led to a way that we can answer that question in calculus. In this video, we're going to look at how can we approximate the area of a plane region just using our geometry tools. And then we'll go on with other videos answering the exact area of a plane region using our topic of calculus. Now here, approximating the area of a plane region, we're going to do this by an example. So we want to approximate the area enclosed by the function f of x equals x squared plus 1 and the x-axis from -1 to +1 x values, and we're going to use n equal 4 rectangles. Now again, I know the area of a rectangle. The formula for finding the area of a rectangle is base times height. And because the sides of a rectangle are line segments and my function f of x equal x squared plus 1 is a curve, we're only going to get an approximate value for the area doing what we're going to discuss in this video. But it will lay the groundwork for us to be able to then continue on with applying our calculus techniques and be able to get the exact area. Now when I look at our graph, our function f of x equals x squared plus 1 is what I've graphed here. And it's from x equal -1 to x equal +1. So I've given some pretty big increments on this so you can see the process. And then our x-axis. So the plane region we're talking about is starting at x equal -1. So I'll draw a vertical line at x equal -1. Ending at x equal +1, so I'll draw a vertical line at x equal +1, the curve and the x-axis. So that enclosed region that we're talking about is this enclosed region here. Now when I want to approximate it using the rectangles, we actually could do the rectangles of taking different endpoints of our subintervals to do this. We could do this by the right endpoints, by the left endpoints, or by the midpoints. And I'll show an example of each of those situations. Now what we do here is we're going to have n equal 4 rectangles, and we want them of equal width for this introductory work with it. So if I take this length of this interval from -1 to 1, and I want to divide it into 4 equal pieces, then that'll give me the increment of x I will use along that interval to break up into our equal subintervals. And always when I'm using this idea to approximate the area using the rectangles, I'm going to follow this step-by-step, 4 steps in order to find it. So first find delta x. Now delta x we find by b minus a over n, where b is the right end of your overall interval and a is the left end of your overall interval. So here my interval starts at -1 and goes to +1. So my a is -1, my b is +1 for this example. So for our example, our delta x is 1 minus a -1 over 4. So that gives me 2 over 4 or 1/2. So then we want to say, well, if I took increments of 1/2 along the x-axis, starting at x equal -1 and ending at x equal +1, what would be my little sub-intervals that I would get along there? So I want to break this interval up into 4 equal subintervals because it asked me that in this question. Well, we're going to do that by starting with our first value of our interval, the beginning of it, our A value, and A is where you start, so I have my -1. And then if I add an increment of a half to -1, -1 plus a half is -1/2. So that's the first subinterval. And then I have -1/2 to, well, -1/2 plus a half is 0. And then I have 0 to 1/2. Then 1/2 plus a half is 1. So those are the 4 subintervals that I would get for this particular example. So I've got -1, -1/2, and then 0, and then +1/2, and then 1 along my x-axis. Now once we have these subintervals, then we're going to look at what we would do for the heights of the rectangles. And this has an asterisk for it because depending on whether we're doing the right endpoints or the left endpoints or the midpoints is what we will do in terms to get our heights of our rectangles. So here's the plan if we are doing first with the right endpoints. Think about your interval. We've broken it up into the subintervals for finding our delta x, b minus a over n. And then in each subinterval, we're going to draw vertical lines up from the endpoints of the subinterval to the curve. Now, in each of these subintervals, I'm going to draw a horizontal line over depending on which of the endpoints we're using. So our first example is going to be with the right endpoints. So look at this first subinterval. I've got my left hand, my right hand. The right hand is pointing to the right endpoint of that first subinterval. Now, if I'm going to do my approximation using the right endpoints, I do the right side, right endpoint for that subinterval, follow it up to the curve, and then wherever that hits the curve, I bring the horizontal line back over to the previous vertical line. So that's going to be my first rectangle from my right endpoint. I'm going to go to the next subinterval, follow the right hand up to the curve, and then draw a horizontal bar back over. Go to the next subinterval, follow my right endpoint up to the curve, draw a horizontal line over to the previous vertical line. And then again, right endpoint up, bring it over and down. And so then I'll get those rectangle areas that I want to add together for doing the right endpoints. So now let's see how we find those areas. So I have my endpoints and I want to find my heights of my rectangles. Well, in my first subinterval, my right endpoint is at the x value of -1/2 for this example. And if I run -1/2 through my function, -1/2 quantity squared is 1/4, and 1/4 plus 1 is 5/4. So this height is going to be 5/4. This point right here is -1/2 went in for the x and 5/4 came out for the y. Then the next point, my right endpoint is 0. 0 goes in for the x. 0 squared plus 1, 1 comes out for the y. So this point is the point 0, 1. The next subinterval, the right endpoint is 1/2. 1/2 goes in for the x. 1/2 squared is 1/4. And then 1 plus 1/4 is 5/4. So that point right there is a positive 1/2 and then 5/4. And then this last one, 1 goes in for the x. 1 squared is 1 plus 1 is 2. So I have 1, 2. So I have first my subintervals. We did that in our first step, we did our delta x. Second step, we did our subintervals. And then for the right endpoints, I plugged negative 1/2 through for the function. I plugged 0 through for the function. I plugged 1/2 through for the function. And I plugged 1 through for the function. So see how that's on the right of each of the subintervals. And we also saw it on the picture too. And then we've got our heights. So our heights of our rectangles for this are f of negative 1/2 is 5/4. F of 0 is 1. F of 1/2 is 5/4. And then f of 1 is 2. Okay, then after we found the heights of the rectangles for our specific case that we were doing, we want to find the area. Now the area approximation well, how do you find the height of a rectangle? You take the base times the height. The base is just the width of your rectangle. That's your delta x. So in this case, that is 1/2. And the height is the function output you got for whichever endpoint you were using. And here we're using the right endpoint. And those heights we got in our part that we wrote down. So we're going to go base, which is 1/2, times your height. And actually we're going to write our function notation for our height first and then our width after, just to kind of lead us into where it will be easier for us to transition when we get to the point of the calculus and we're getting the actual area. So I'll write it out in function notation and then put the numbers in. So we have f of negative 1/2 times 1/2 plus f of 0 times 1/2, then plus f of 1/2 times 1/2, and then lastly plus f of 1 times 1/2. So my height times my width plus my height times my width plus my height times my width plus my height times my width. Now there was the notation for the height. Now we're actually going to put the numbers in there. So f of negative 1/2, that's 5/4. So I have 5/4 times 1/2 plus f of 0, that's 1. So I have 1 times 1/2 plus f of 1/2 is 5/4. So I have 5/4 times 1/2. And then plus f of 1 is 2. So I have 2 times 1/2. And so we get from this 5/8 plus, and I'm going to put everything in eighths to get our fractional value. So 5/8 plus, well, this will be 1/2, but that'll be 4/8. And then plus 5/8. And then plus, this is 1, which is 8/8. So then 5/8 plus 4/8 is 9/8. And then I'll get plus 5/8 is 14/8, and then plus 8/8 is going to give me 22/8. Or 11/4. So there would be 11/4 square units of area that we're approximating to be caught between that curve, the x-axis, over that interval. Okay, let's now look at what we would get for the left end points. So for the left end points, we're going to come back over to the picture and we're going to look at what we would get for that. So here, we're going to the heights of the rectangles that we've drawn in, just to get a cleaner space to start from. I'm going to leave our function values there because we're going to actually use the part of those, most of them. But then again, we've got our vertical lines at our sub-interval start and end, and I hadn't run our -1 through our function. So if you put -1 through your function, you get out -1 squared is 1 plus 1 is 2 for that dot. Now, left endpoints, that's this left hand. We're going to follow it up to the dot, horizontal over, and then back down. So that rectangle. And then left endpoint, follow it up to the curve, horizontally over to the right, and back down. Left endpoint is 0, followed up to the curve, over and down. Left endpoint up to the curve, follow it over and down. So that's the picture you would draw if someone asked you to draw an illustration of approximating the area using the left endpoints. So how can we do it with our intervals that are set up? Well, with the left endpoints, here's your first subinterval. This is the left endpoint of the first subinterval. And then I have my -1/2 is the left endpoint of the second subinterval. 0 is the left endpoint of the third subinterval, and 1/2 is the left endpoint of the fourth subinterval. Now notice, because these subintervals touch, where the first one left off, the second one picks up, we have that occurring as we go, except for the start and for the end. So what was the right endpoint of the first subinterval is the left endpoint of the second subinterval. So what was the right endpoint of this first subinterval is the left endpoint of the second subinterval. So some of these function values are going to be the same as we go through. Now the arrows are the ones we're looking at. We want to do our left endpoints. Our heights are f of -1, which came out to be 2. F of -1/2, which came out to be 5/4. F of 0, which is 1. And then F of 1/2, which is 5/4. So notice that we're going to stop at the 1/2 for our left endpoints as we go through there. Okay, so now our area approximation . Remember, for each rectangle, it's height times the width is how we're going to write it, so that we have that thought process notation where we're going to transition to later. So for my first rectangle, my height is 2 and my width is that delta x, which is 1/2. For the second rectangle, using the left endpoint, my height is 5/4 and my delta x width is 1/2. And then the next one, my height is 1 and my delta x width is 1/2. And then for the last one, my height is 5/4 and my delta x width is 1/2. And now when we go through this, again, my common denominator is going to be 8. So I'll go ahead and change it into 8s. So my first term, 2 times 1/2 is 1, but written as 8s, that's 8/8. Plus 5/4 times 1/2 is 5/8. Plus, and then 1/2 in 8s is 4/8. And 5/8. So for this one, I do again get my 22/8, which is 11/4. That does not always happen. It's happening for this example because I have my interval equally spaced on either side of the origin for an even function. But it worked out well with running the numbers through and things. So often, most generally, these will not be the same number. They just by happenstance are this particular time. Now, just kind of a notation thing, if I were writing this in general, our sub-interval notation as we go through, and I guess I'll put it over here on the picture, our A is the same as x sub 0. My starting x value is my A, the beginning of the interval. And then my x sub 1, I get by taking that start value A and adding a delta x to it. And we said it, I just didn't write the notation down at that moment. And then my x sub 2, I start with my start number A and add 2 delta x's. My x sub 3, I start with my A and add 3 delta x's. And then finally my x sub 4 in this case, I have my start number A and add 4 delta x's. And when you get to that coefficient being the same as your n for the problem, you will land on B. You will land on that end of the original interval. And if you don't, you did something wrong with the calculations of your subintervals. So go back and double check your work. And then for each of these functions, these f of values, these f of the quantities would be of the notation we have here when we get to the video that goes a little bit more in depth with the notation.